Very good morning. We are discussing on principal component analysis. Today's topic is model adequacy test and interpretation. We start with the examples what we have discussed in the last class. Then we will show you sampling distribution of eigenvalues and eigenvectors. Under this expected value, covariance, confidence interval and confidence region will be discussed. Let us go to the next slide. We will continue with PCA, and today we will discuss PCA, model adequacy and interpretation. So last class we have discussed up to extraction of PCA, extraction of principal component, and we have seen that first we have used S minus lambda I determined equal to 0, then we got the eigenvalues, and then using individual, suppose for the first one A1, first eigenvalue with the first eigenvector we have found out, and subject to A1 transpose A1 equal to 1. So similarly you can find out A2 using S minus lambda 2 A2 equal to 0 and A2 transpose A2 equal to 1. In this same manner you will be able to find out the eigenvectors. Once you estimate the eigenvalues and eigenvectors, you can write down the equations also. For example, the example we have considered here, that the loadings we are calculating from profit and sales are the two variables, interrelated variables, and we have extracted also two component PC1, PC2, and these are all Z1, Z2, and the loadings, that basically this component loading or the eigenvectors 0.19 and 0.98 for your first one, that your component 1, 0.19 x1, 0.98 x2, and similarly for Z2 it is 0.98 x1 minus 0.19 x2. You see ultimately what is happening here, just reverse, only one sign reversal is there. So what I ask you that you please compute in detail using this matrix, S matrix, like 1.15, 5.76 and 5.76, 29.54. You compute in detail and you come to up to this level, you will be able to find out why, what is the reason of this type of relationships. Now under adequacy test, what we want to discuss first, we have identified lambda 1, I think it is 30 point something, 66 probably, 66, and lambda 2 is 0.03. Okay. Then the total is sum total of lambda j equal to 1 to 2 here, this equal to 30.69. Now we have extracted this from this S matrix. Now what is the stress of S? Stress of S is the sum total of the diagonal elements. This is 1.15 into 29.54 is not, this is 30.69. This is 30.69. Okay. Now if there are, if S is P cross P matrix, then you will be getting like this. Suppose we are using sample S11, S22 like this SPP. Other way you can write S11 equal to S1 square, S2 square like this SP square, that you will be getting, and definitely there are off diagonal values are also there. But stress is this. So, I can say stress of S is nothing but sum total J equal to 1 to P Sj square. Okay. So, this can be proved that your sum total of lambda j, j equal to 1 to P equal to sum total of j Sj square. Sum total of, that means the variability, if you extract the maximum number of eigenvalues, and then what you will find out that sum total of this eigenvalues will be sum total of the variance component of the original matrix S matrix what you have considered. Okay. And you have already also found out one another thing. Suppose I said that variance of A j transpose x, this one also we found out that A j transpose S A j. So, now if I want to know what is the variance of Z1, that will be variance of A1 transpose x, which is A1 transpose S A1. It should be lambda 1. It will be lambda 1. How? What is your A1? In this case, A1 is 0.19, 0.98, S is 1.15, 5.76, then 5.76 and your 29.54. So, just you do this multiplication, you will find out, that is A1 transpose S A1. You find out, because this one you see A1 transpose is 1 cross 2, 2 cross 2, 2 cross 1. So, resultant will be 1 cross 1, and definitely this will be 30.66, which is
S A1 is lambda A1, and if we can take lambda, since lambda 1 is a scalar, we can take lambda outside and A1.
That you can do also, that is also possible. Basically what I am saying, suppose if you create a diagonal matrix of lambda, that is lambda 1 all 0, lambda 2, then lambda p, then what you can write basically is sum total of this one, I think that Sj square, j equal to 1 to P Sj square, that you can write stress of your lambda A lambda, I think A transpose, that you can be, it can be written like this. Now, you will, what you will do basically, you why I am using A, because we have started with this, and then lambda, this is the transformation matrix. So, it will be lambda transpose your A, trace of this. Now, A transpose A, this is orthogonal I. So, trace of lambda into I, this will be trace of lambda, that means diagonal elements. So, sum total of j equal to 1 to P lambda j square. So, this is what is the decomposition. Lambda j square, j equal to 1 to P equal to Sj square.
It's not square, I think.
Lambda j. Lambda j. If you go for singular value decomposition, then that will be that square will be there. Okay, fine. So, this is the case. So, I think you now understand that the relationships, everything is these are known. What is next? Next is, as I was telling you, suppose you got lambda 1 equal to 30.66, lambda 2 equal to 0.03. These are point estimates, because we have taken a sample S, that 2 by 2 matrix from n equal to certain values. I think our case n equal to 12, 2 variables values here. Suppose if I go for next time, as I told you earlier also. So, point estimate if you want to find out, then we are going for expected value of lambda j, let it is the theta j. That means, we are saying that in the population principal component, if you analysis if you do, there you will be getting the, if you know the everything about the population, you will be getting the exact value of that eigenvalue for that particular population. This is coming from sample, this is from population. So, this is one. Second is covariance of lambda j, lambda k, this will be 2 theta j square by n minus 1 for j equal to k and 0 for j not equal to k. So, this is the development. So, what I mean to say here then, that means the two lambda components, lambda j and lambda k, they are variably when k j equal to k, this is nothing but the variance component, and that when j not equal to k, that is the covariance component. So, covariance is 0, variance is 2 theta j square by like this. Now, we can assume that this will follow a normal distribution with theta j and 2 theta j square by 2 theta j square by n minus 1. If you when that means you know the distribution. Now, how this distribution is coming, that is definitely a question, but it is a complicated issue. So, there are several researchers, statisticians developed this. So, we are sticking to this, that this means lambda j can be approximated to normal distribution, and provided definitely n is large, provided n is large. Now, when this is the situation, can you not find out the your that confidence interval for theta j? So, what we will do basically, you want to find out this minus z alpha by 2 plus z alpha by 2. We know that lambda j minus expected value of lambda j by standard error of lambda j, this follows z 0 1, that basic statistics, that concept. So, that means lambda j minus theta j. Now, what is the standard error of lambda j? Now, what is the value here? That variance part 2 theta j square by n minus 1. So, that means standard error, if you write down here, this will be 2 theta j square by n minus 1. Now, this quantity will be this side minus z alpha by 2, this side plus z alpha by 2. Okay. So, ultimately this one can be written like this, z alpha by 2 less than lambda j minus theta j by theta j will come out root over 2 by n minus 1 less than z alpha by 2. You do now mathematical manipulation, then ultimately what you will get, you want something like this, getting me? So, theta j will come out here, then this theta j is there. So, this theta j plus this quantity will be added, and then as it is within this, so 1 by something will come. Final form will be like this, 1 plus z alpha by 2 2 by n minus 1, then 1 by 1 minus z alpha by 2 2 by n minus 1, but we have this lambda j component. So, it will be lambda j, it will be lambda j into lambda j you can write. Correct. If our alpha value is 0.05, then alpha by 2 will be 0.025, then z alpha by 2, this will be 1.96. Now, we got 30, our lambda 1 value is 30.66 divided by 1 plus 1.96 into 2 by 11, n is 12, less than equal to, also you can write this way, we write less than equal to 30.66 divided by 1 minus 1.96, 2 by 11. Okay. So, ultimately this quantity will yield that 30.66 by 1.836 less than equal to theta j less than equal to 30.66 by your 1 minus this 0.0164, and this leads to 16.70 less than theta 1, because we are considering j equal to 1, j equal to 1. So, if I write theta j also j equal to 1 here, then this value is 186.95. But do you agree this? Do you agree with this? The reason is your original, see, your original data, sample data, if you see that the total is I think 30.69, this is the total variability. Now, if the see range is very high, it is because of many things, your number of variables is not, number of observation is very small. So, this is a huge difference. So, that means sticking to that first one, point estimate one only, that point estimate will okay, it is okay, all practical purposes it will serve the what you want to do, but see that this much variability for the population PCA is there, if I go by this simple sample PCA.
When n is very large,
Then this is true, then this true result, because we are saying that this is possible when n is large, when we are assuming normal distribution, when n is large. Our case n is very small value, so we cannot say that this is correct, but this is the way you will be finding out the confidence interval for the population eigenvalue. Okay. Now, another one is that you also similarly using S, that we found out that Aj, what is this, Zj equal to Aj transpose X. Now, this Aj you have found out the value of Aj, but this that is sample Aj. Correspondingly in population, suppose this is lambda j is there, that is this is the eigenvectors vector from sample, this is population eigenvector, jth eigenvector, population jth eigenvector. So, similarly there is definitely the distribution possible, but that distribution again really these are all complicated distribution. What it says that the eigenvector what you compute, this follows multivariate normal with Aj and Tj, where Tj is theta j by n minus 1 sum total of k equal to 1 to p and j not equal to k, theta k by theta k minus theta j square lambda k transpose, not lambda, that is alpha k transpose. This alpha is what? This one. Okay. So, as we are using here alpha k, okay, we are saying k equal to 1 to p, this type of big equation will come. Just for the sake of clarification, I request all of you to check this, that k and jth term, the notation, if there is, just check this one. Okay. So, ultimately as we are getting that NP Aj Tj, that is the multivariate normal, you will be getting 100 into 1 minus alpha percent confidence region, because it is p variable case, you will be getting the confidence region, and that confidence region takes this form n minus 1 alpha j transpose lambda j S inverse plus lambda j inverse S minus 2i into lambda j, that follows chi square p minus 1 alpha. This is the confidence region. So, I am repeat that 1 n minus 1 alpha j transpose lambda j S inverse plus lambda j inverse S minus 2i. This I is basically, if S is p cross p, then I is also p cross p, that is the identity matrix. Then this quantity will follow this distribution chi square p minus 1 with alpha. You can check this also, confidence region, all those things. And now as it is confidence region, you may be interested to know the simultaneous confidence interval. Then you require to simplify it further, but these are really complex issues. But I am giving you basically what you have applied your PCA, that is from sample. Now, what is the guarantee that suppose in the texture direction what you are trying to find out, that you are actually going for the true, what is your sample size? It is quite large?
Yes.
Very large. Very large. So, we are, I think you can still check the particularly the confidence interval for lambda j eigenvalues. That means the dispersion must be checked, and if it is very, I think it will be within the limit, because when n is large. Okay. So,
image of size 128 cross 128, then we have 128 into 128, this much data.
no, what is this 128?
128 into 128.
No, I understand, but 120, this is a matrix, 128 cross 128. What about n? What is n? Total observations.
Total is 128 into
128 into 128. So, these many observations are there. It is a quite large object. Okay. So, I think that as you are doing it, maybe you will be we will be finding papers where this dispersion measures for the eigenvalues, that is not considered. That means uncertainty part is not considered. So, you can propose, your adequacy will be much better. You can propose that okay, and maybe different sample size, how the adequacy that your fitness will change, that can be also a good addition, theoretical contribution. Okay. Now, let us see this what is that example. Now, see what happened ultimately, lambda 1 is this and ultimately this is what is our confidence region. And you have seen in multivariate normal distribution case the exponent term, that same thing it is basically. When I am talking about that that your AJ is multivariate normal, for two variable case the ellipse is formed. Ellipse is formed. So, you find out the confidence ellipse for your eigenvector. Okay. Okay, thank you very much.